Hi. All right, so let me tell you about these homology groups. There's a it's fairly complicated, and there's a lot of groups in this section. So I went through the notes and added some extra notes. And the first thing you notice there on the left is that it says you can switch to page 3. Start there to read some of the definitions first and then come back to this beginning point. This beginning point, though, I'll start here, tries to make it a little more familiar by starting with an example that we've seen before. First, the intuitive examples of finding the boundary of a topological space. Just some easy topological spaces. The boundary of a two-disk there is the circle that's around it, and that's S1. Then take that as the space and look at the boundary of S1. Now, S1 itself has no boundary. You can think of it as the fact that the circle has no end points. It goes around forever as you follow that circle. So it has an empty boundary. The same thing is also true of a single dot. It has an empty boundary. And the important point to notice here is that when you take boundaries twice in a row, the boundary of a boundary, you get something that's empty. For that dot, if you take the boundary of a line segment, you get two dots, 2 points. And then if you take their boundaries, both of them are empty. That's going to be really useful. Now, let's look at an example so we can see some boundaries and what we mean by taking the boundaries of a cell complex. This is the real projective plane P2 that we've seen before. I labeled the line segments A and B. Those are actually glued together. B is glued to the other double arrow, and A is glued to the other single arrow. Here's some things that we worked out before. For instance, the Euler characteristic is 2 minus 2 plus 1 because there are two corners, x and y, and then minus 2 for the two line segments, and then plus 1 for the two cell, the two disk, which I called A here. Then we could also find the fundamental group of P2. Then, though, we have to use loops. I can't use those line segments, so I labeled a loop C that goes from x to x. And C is equal to C inverse. As you go through the two cell, if you homotope C through the two cell, you end up at the other side of the square, which runs the double arrow in reverse and then the single arrow in forwards, the opposite direction that it did if you followed the arrows closest to C. So C equals C inverse. Remember, that means that it turns out to be the integers mod 2. So in homology groups, you get to do something that we would have liked to have done before, which is we get to begin with, we get to start by using those edges that we glue as the generators instead of being forced to look for a loop. In fact, we're going to make a bunch of groups, and we're going to use the cells of all dimensions, all the disks, D0s, D1s, D2s, D3s, etc., as generators. We'll make one group for each dimension that we'll see on page 3. They don't have to be loops like in Pi 1. Another difference from Pi 1 is that we're going to start by requiring that the group operation is commutative, like addition. So all the groups are going to be abelian. They're forced to be abelian groups. But the operation then is not going to be concatenation of loops anymore as it was for the Pi 1. Instead, the operation is going to be purely formal. We're just going to add two cells of the same dimension without any geometric meaning, just like putting together a word out of letters, but without any geometric meaning this time. And we'll mention that on page 3 again. Now that I needed to say here though, because we want to take that boundary function. Remember, it looks like the partial derivative, but that's a good reason for that, since it obeys a sort of Leibniz rule we saw before. We won't use that right here, but we do want a boundary function, and we want it to be on those groups where we're using all of the cells as the group generators, that it does what it intuitively should. But that means we need it to make sure that things cancel correctly. The key is to use an orientation. We'll look at the orientation of the D2, the disk, up in the picture above. And we'll pick counterclockwise. We could actually pick either orientation of that disk, but counterclockwise works nicely. Then we'll say the boundary of A, that disk, is A inverse B, A inverse B. So let's see, I can go back and look at the picture real quickly. So if I'm saying A inverse B, A inverse B, it looks like I started at X and followed the edge of that 2 disk around all the way back to X. A inverse B, A inverse B, and that's the whole boundary of A. And it is equal to E, the identity, in pi 1. Okay, now that's the boundary in the fundamental group, but we're not going to be doing that in the fundamental group now. We want this to show up in the homology group. And in the homology group, the boundary of A is going to be negative A plus B minus A plus B. I just changed the inverses to minuses and the multiplication to addition, but other than that, it's the same thing. So for a 2-cell, the boundary is the same thing as the relation in the fundamental group, in the format where the relation is solved for E. It's just written in additive notation. And we did pick a starting point. We picked X, but that's arbitrary. We could pick any starting point.